Hey everybody, and welcome back to another edition of Can You Hack It? I am your host Ben, and this week we are back on Hackthebox.eu, this time looking at a box called Smasher. And so this is a Linux box with a pretty high level of difficulty. This is actually probably the most difficult box that I've actually done on here. And it was also the most enjoyable. It had a lot of stuff that you don't typically see on most of the boxes on here. So anyway, we'll dig into it. Just to give you forewarning, this video is going to be shot in multiple parts and then stitched together. Hopefully you won't notice, but if you notice some incongruity between different screens or something, it's probably because of that. Reason for that is I expect this to be a fairly long video because it's fairly complex, and I wanted to include some of the stuff I originally did that didn't work, because that's how you learn, is seeing, the different ways you try stuff. If I was to just show you the things that worked, I could make it shorter, but it wouldn't be as educational. And after all, educating is the point. So with that warning, I will make sure that I put quick links below in the description so that you can jump around to spots that interest you, skip the ones that don't. I'll try and also mark things that were failures. That way, if you don't want to see the failures, you can just skip ahead to different sections. So anyway, let's go ahead and get started. And so, actually, I minimized that a little prematurely so we can see the IP address of the box is 10.10.10.89. So if we just get an Nmap going, oops. And T5 makes the timing aggressive. SC and SV enumerate scripts and versions. V gives us verbose output so that we can see while it's running. OA is output all formats, and we'll write those to Nmap quick. And then, of course, the IP address of the box, which is 10.10.10.89. I'm actually not connected yet, so let me fix that real quick. All right, so now we should be connected. And so we see TCP is open and port 111 is open. So, or sorry, did I say port TCP? SSH on port 22. Is open, and 1111 TCP port is also open, which at this point we don't know what that is, but we should see in just a second. And so we've finished up now, and we can see that port 1111 is identifying as LM social server. And we can also see here that the server is being listed as shenfang-tiny-webserver. So we just copy that. We'll paste that, search for it real quick. While that's searching though, let's take a look at the actual site and see what we have there. So 10.10.10.89, port 111. Looks like we just have a directory listing, and we list index.html. If we click on that, we have some sort of a login. Once our email, test.com. If we have a password, let's see what it does. Doesn't actually seem to do anything. And so let's go ahead and get gofuzz going in the background, and we'll continue looking manually. So if we run gofuzz with -w, use our standard word list, which is the dirbuster 2.3 medium. Directory list 2.3 medium. Do 100 threads. Hide response codes of 404. Be recursive and show full responses. 10.10.10.89:1111/fuzz. And I mistyped something. Show full responses. Connection reset by peer. There we go. So now that that is running, let's go back to this shenfang-tiny-webserver. It looks like it has a GitHub page. It looks like a tiny web server written in C. Features seem pretty basic. no security check, so that's interesting. Let's take the source code here, go to raw, we'll copy that and we'll paste it into Sublime Text, and then we will save that in our current working directory. Let's see, CTFs, hack the box, videos, smasher, and we'll save this as tiny.c. And we'll look through that in just a second. So the fact that it said it has no security checks makes me wonder if we can do something like directory traversal. So we did slash dot dot slash, drop down a few directories and then get etc password. It seems to just be sitting here. Wonder if our gofuzz is, these response times are incredibly long, 11 seconds, so I think maybe we're overloading the little web server, so if I cancel those out, see if it gets any better. While that's going, let's start at Burp so that we can have a little more control over the requests that are sent. We'll just do a temporary session with the standard, or the default settings. We will turn intercept off, and then we will switch this over so that we're using our Burp proxy. And it's possible gofuzz caused the server to have a heart attack, so I may need to actually reboot it. See if our history's here. Looks like the browser's munging our requests, so let's send this to repeater and let's make sure that that's included. Still not returning, so I'm guessing that I caused an issue with the web server, so we'll go ahead and reset the box. Okay, and so let's just try sending this again. And we can see that we are able to do directory traversal, so we're able to get a list of users here. We can see that the only users, it looks like, that are not system accounts are www, smasher, and root, of course. So we will keep that in mind. In fact, let's just open up a quick tab. Oops, not a new window, a new tab. And we'll smasher, www, root. And so let's go ahead and see what else we're able to find here then. First things first, let's see if we can see, or which directories we're able to see. We may be able to just do this also instead of dropping down. So that does work. Looks like www is our only user that we're able to see the home directory of. We can probably go back into this window since that works. So we just double slash it home. So we've got www. Let's go ahead and turn off Burp also. And so we've got some stuff in here. Before we look at that, let's do www/.ssh and see if he has an SSH directory that we can get into. It doesn't look like it. So it's not as simple as just stealing a SSH key. Let's see if we can find out a little bit more about what this system is. So if we do //etc issue, I think, we should be able to see what version of Ubuntu it is. Or I'm guessing it's Ubuntu. Looks like it is. It's 16.04.4 LTS. Users. Clean this up a little bit. Okay, and then we can see if we can find out a little more info. I think Etsy Debian version maybe, Debian version. Stretch. iOS release works also, which probably has the most info. If it's got it. Hopefully somebody else isn't on this box and causing issues. It seems a little weird since we're not running gofuzz in the background that the web server seems to be hanging again. Here we go. And so it looks like it is Xennial. And let's see, we should be able to see like Etsy hostname to see what the host name of the box is. Smasher, which is what I assumed since that's the name of the box. So we've got a user Smasher, the box name is also Smasher. And so let's go back to that user's home directory, which was home www. And we see a restart sh, which we can't grab for some reason. See a tiny.webserver directory, which we can't get to all of a sudden either. I think somebody else is unfortunately on this box, because we should definitely be able to get into here. Oh, that's weird. So that worked. Why is... Oh, probably because I didn't have the trailing slash on there and it was doing some weirdness where it was just replacing it. So we try again. So restart.sh looks like it switches to that directory. It does a kill on anything with the name tiny in it, on any process. And then it does a no-hup tiny with the folder public HTML. 1111 is the port, redirects standard error and standard out to dev null, and then it backgrounds it. So let's take a look at the tiny.webserver directory. Looks like we have a make file, which is building tiny using, let's see, compile wall, O2 for optimizations, the no stack protector, so we're not using canaries or stack cookies. Exec stack, so the stack is executable. And then everything else is pretty default. So this makes me think that possibly we have some sort of buffer overflow in here, because it looks like they're trying to make our lives easier by compiling it with these default protections disabled. And so let's go ahead and in our directory here, let's pull down that tiny file. So wget http://10.10.10.89 1111 /home www tiny web server tiny. And then let's rename that. We'll make it tiny-smasher so that we know that it came from Smasher. Because since we have the source code, we'll take a look real quick and see. But if it's multi-threaded, we probably want to see if we can easily disable that, because it'll make it easier to debug. But first, let's just see with this one if we can, if it does have some sort of buffer overflow. So if we do /tiny, we gotta make it executable first. Tiny smasher, and then /tiny smasher 1111. And then let's do a dmessage in this window so that we can see if we get any Any segmentation faults? I forget what the flag is. There's a flag to just tail it, basically. Which is -w, it looks like. So dmessage -w. Put some spaces in there. And then finally, we will do a wget, or actually let's use curl. Curl localhost 1111 / and then we'll do like Python -c print a times 1024. And this is just a random number that I'm picking. You could pick anything. You'd want to increase this if it didn't do anything until you get to a point where it doesn't seem reasonable that it's going to cause a crash. So we get the message file not found, which is presumably coming back from the web server. If we switch over here, we see a bunch of our A's. We don't see any sign that it crashed. However, if we do look at dmessage, we do see that it actually caused a general protection fault. So we probably are getting a buffer overflow. The instruction pointer was pointing to a legitimate address, most likely, so we didn't actually overwrite the instruction pointer. The reason for that I'll point out in a second, but basically it's on 64-bit systems. Overriding with all A's won't work. So let's go ahead and see, let's load up Tiny in GDB and check some stuff. So GDB Tiny Smasher. And if you notice on my GDB, I'm running PEDA, which is a Python enhancement to GDB. Super useful. Make sure that you have it installed if you're doing any of this stuff. I'm not going to cover it on this just because, again, it's going to take too long, but if you Google PEDA debugging or something like that, you'll come into the GitHub page. There's great instructions for how to install it. It's super simple. You just run a few lines and everything's done. So first things first, we just do check sec. What this shows us is what security features are enabled on this executable. And so we can see that stack cookies or canaries are disabled. Fortify is enabled. In this case, it's not really going to matter for us because all Fortify does, as far as I'm aware, is it swaps out insecure versions of function calls and libraries for their secure counterparts. But in the case of a buffer overflow, the fact that it's happening right now shows that whatever Fortify is doing isn't helping protect against it, most likely. NX is making the stack not executable, which we already saw in the compile or the make file. That's disabled, so that's why we see that. PIE is position independent executable. That's a newer technology where when you compile it, where the library calls and stuff are, I think, or where some of the functions are. Anyway, they're randomized, and so it makes it harder to use known addresses and use some of the attacks that we would normally use, which I'll actually be covering later, like return to libc attacks. And then Railrow is relocate read only, I think, or something. Anyway, I don't know exactly what it is, and in this case it's not relevant, so we'll just skip over it. Debugging and exploit development is not my strongest point, so some of these things you'll notice I don't know what they are. I'm not going to look them up right now just because we're going to be so time constrained. And so what we can do now is jump back out of this real quick and just do a file on Smasher, Tiny Smasher. So we can see it's a 64-bit LSB executable, which is good. If it wasn't, if Pi was enabled, we would see like Pi executable here, or sometimes I think instead of executable, it'll say shared library or something along those lines. So now let's see if we can start building a exploit against this. So we'll switch back to our tiny.c code. I'm gonna try and go through this fairly quickly. As of right now, we don't really know where the buffer overflow is, and it's probably not going to be as simple as looking for known functions like string copy, strcpy, yeah, things like that. So what we're going to do instead for now is we're just going to, actually we ended up, I think, about where I wanted to be. So we've got main here, and if we look towards the bottom of main, right here, we can see that we're basically forking off 10 versions of this, and that's how we're having a bunch of threads to handle requests. We don't want that in this case because it makes it a little more difficult to debug with GDB. So, or at least it does for me. I'm sure if you know the tricks, it doesn't. But I had issues previously, even once I did things like enabled set debug, or sorry, detach on fork to off, and can't think of the other one, but there's another one that helps you follow things when they fork, but it still didn't work too well. And so I found it was just easiest to comment out this loop here so that we're only dealing with one thread handling requests. So if we save that and we go back here, we can build it. So if we do gcc, and then we need to do fno stack protector, and we need to do no PIE, and then z exec stack. We'll output it, we'll call it tiny.st for tiny single thread, and then tiny.c is our input file. And so that compiled just fine. And so now let's try and run that real quick. /tinyst1111. We go back to our curl window, send it again, file not found. This time we seg faulted and bumped out because we've only got that single thread. And so this should be easier to debug then. So we go to GDB and do tinyst. And then let's do start 1111, which will start the process. It'll break automatically in main at the first instruction, so we'll do C to continue. Now we see it's listening on port 111. File descriptor is 3. So if we send it again, file not found. We can see we seg faulted here. And this, by the way, this display that you get here, this is one of the things that PETA is buying you. And so we can see that the stack, which is what it's showing here, is filled with a bunch of A's. We can see that the stack pointer, which RSP is a 64-bit stack pointer, it is got the address of a bunch of those A's. We can see that RIP, which is our instruction pointer, if it was 32-bit, it would be EIP. It's still set to a valid address. It looks like it's inside of the process function called 426, so that's the return from process, as we can see right here. And the reason we can't overwrite that is that instruction pointers in 64-bit aren't actually 64 bits long. They're 48, I believe. And so all A's isn't legitimate because the top 4 bytes, or sorry, the top 2 bytes need to be zeros. And so let's pop back to the source code now, since we see that it's happening when process is trying to return. Then that lets us know that it's probably somewhere right before that, or somewhere inside of process. So here's process. So we can see it does a log access, closes this FFD, which is a file descriptor probably. So it handles some stuff on the file stats. Depending on if it's a regular file or a directory, it does one or the other. Otherwise, it returns a 400 unknown error. And if it's equal to 0, it returns a 404 because the file wasn't found. And so above that, we see it's got a function called parse request, and it's being passed this HTTP request structure and a file descriptor, which the file descriptor, it looks like, is probably our network socket. So it's being passed the network socket's file descriptor, and it's being passed this request structure. And so that's parse request. And so if we scroll up, we see parse request here. And if we look here, we're creating some buffers. These buffers are all set to size max line, which max line is 1024. And so, oops, sorry, lost my place. So those are all 1024. We're setting some offsets. We're setting the end. We're doing a read init where we're passing this RIO structure in the file descriptor, RIO buffer, which is this empty buffer and max line. So that's probably doing a read up to max line into buff. That's probably not a problem because max line is 1024 and this buffer is set at 1024. scanf, it looks like we're grabbing a couple of the things, but we apparently don't care about versions, so we're not populating that. We're populating method and URI, which again are buffers of up to 1024 bytes. Doing a read all where we read line, we're reading into buff, max line to 1024 again. If buff 0 is equal to either R, A, or N, or sorry, index 0 is equal to capital R, and index 1 is equal to A, and 2 is equal to N, and it looks like it's doing some range copy, I guess. So again, nothing looks too out of the ordinary there. If URI 0 is equal to a slash, then the file name is equal to URI plus 1, so it's getting everything after the slash. Again, nothing probably interesting there, so that leaves us with URL decode. URL decode's being passed file name. It's being passed file name from that request structure that we saw, and then it's being passed max line, which is the 1024. And so let's see real quick what this request looks like. It's probably up top. Yeah, it's right here. So HTTP request has a buffer of 512 bytes. That's where our problem is probably, and then an offset and an end. So if I go back to where we were, apparently the wrong place, go back to decode or URL decode. So URL decode is being passed right here. Where's it at? Right here. So it's being passed file name. This is a 1024 byte buffer. It's being passed this 512 byte buffer, and it's being passed the value of 1024. And so if we look here, that's our source, our destination, and our max. And so our destination is that 512 byte buffer. And you can see here that it's doing a URL decode on any URL encoded stuff. So if it has the percentage, then it's taking the value of the next 2 bytes. Otherwise, it's just doing a byte for byte copy. And then when that's all done and max has been decremented to 0, it's appending a null byte. And so the problem we're going to get here is that we're copying 512 bytes too much information into that destination buffer. So we're overwriting 512 bytes of who knows what on the stack. And so because of that, we'll be able to overwrite the saved return pointer, which is what we're hitting when we exit out of process. And so then we should be able to control the flow of the program. So let's see if we can do a little test to prove to ourselves that we're correct here. So if we do a disassemble process, let's set a break at process plus 426, which is this return instruction here at the end of the function. So our breakpoint set, we'll do a start 1111, continue. And so now we're waiting and ready to go. And then we'll pop over to one of our other windows here. Use this one, and we'll create a pattern using a tool that's in Metasploit. So we do msf pattern create, I think. Length, we'll do 1024, and we'll output that to pattern.text. And what this is going to do is create a pattern that has no repeating parts in it, so we'll be able to use that to figure out how many bytes we get till we hit the instruction pointer. And so if we cat that, pattern.text, you can see it there. So what we can do then is we can use that in our curl statement. We can just do curl, and then inside the backticks, we'll do cat pattern.text. We get file not found. We hit our breakpoint in process. We can see now this big string at the top of the stack. We can see RSP is pointing to a spot at it. So what we can do is we can do x/xg, which gets us the 64-bit value that's at whatever address we ask for. And so we can ask for RSP, which is the stack pointer. And so we get this value. We can take this, copy it, go back over to here, do msf pattern locate or offset q for query, paste in that value, and it should tell us where it's at. So 568 bytes. And so then what we can do now is take that 568 bytes and we can actually try and do a simple test to see if we can get overwrite of the instruction pointer. So let's come back here. Let's start this back up. 1111. Continue. Let's go back over here. Let's go back to our Python command. Let's print 568 A's this time. And then what we'll do is add another B times 6. And so that'll get us our 48 bytes of B. And I think that should work, other than I put the wrong quote on there. Use the double quotes. Oops. Use capital B. So this should get us 568 A's and 6 B's. The other two bytes will automatically be zeros because of it being little endian. They'll flip to the front, and so we should be good. So we get file not found. And as you can see here now, our stack pointer is pointing at 48 bytes of 42, 42, 42, 42, which is our B's. So our 6 B's. So if we just do a next to step to the next instruction, so we actually return this RSP value should be popped onto our IP. And so you can see here, our IP is now set to BBBBB. And so we have control of the instruction pointer. So far, so good. So we continue again. We should just get a seg fault, which we do because we're not pointing to a valid place in memory. You can see the 2 bytes there that are set to zeros. The rest of them are set to 42s. And that's not a valid place to execute from, so we seg fault. Now, one thing that we aren't able to tell on this system is whether or not some of the security features are enabled. So if we do proc sys kernel randomize va space, and we basically get a blank page. I didn't really dig into this here. I probably should have, but it's back in the source code. Anyway, we're only able to read regular type of files. We're not able to read any of the proc file system stuff. So whether or not randomization's turned on, we don't know. What we'll do locally is we'll turn it off on our local box, hoping that that's the way it is on the remote box because they disabled all the other security features. This one's more a system specific, so each time the process is executed, its addresses are randomized. But most likely it's going to be on the real box. But just for the sake of the video, I'll show how you would do it if it wasn't on. So we'll disable it on the local system. We'll try it on the remote system. If it fails, we'll move on to another technique. So back in this other window, let's do syscontrol kernel.randomize va space. It's set to 2, which means it's enabled. We'll set it to 0. Check it again. So now it's disabled. There's no reboot needed. This takes effect immediately next time you launch the application. I don't think we need to actually quit out of here, but we'll quit out anyway, just in case. So now we're back up and ready to go. So there's a few steps to this. We'll start this 1111. And actually, before we continue from this breakpoint, let's put a breakpoint at process plus 426 again. Now we'll continue. So now we're listening and waiting. Now what we're going to need to do next is build a quick payload. In order to do that for our shellcode, easiest thing to do is msfvenom. So if we do architecture x64, platform is Linux, payload is Linux, Linux, sorry, mistyping a bunch. Linux x64 shell reverse TCP, lhost is equal to 127.0.0.1, and lport is equal to 4444, and then format's Python, and actually I'm going to change ifconfig. We will use this address for our lhost. I've had problems before for some reason where localhost causes issues. So this should output the shellcode in a format that we can just use directly in Python. I like to get the line that I used to create it also. The reason for that, as I'll show in a second, is you can comment it out, and then if you ever come and look at this code again, you don't just have magic shellcode that you have no idea what it is. So if we pop open another tab again, we'll paste that in, knock it down a couple lines. We'll comment out all these parts. Oops, I hit too many. Something weird's going on. Oh, I see what's going on, okay. So we'll comment those out. It's just because this line's wrapping at the top that it's creating some weirdness. We'll set to Python here so that we get our nice color coding. And so we're going to need to import pack from struct. So we'll do from struct import. We'll just import everything. Import socket. Reason we need to import socket is because we're trying to talk to it, to that remote server, or in this case local. We could also just output to a file and then spit that file into it using curl, but I don't like doing that because of issues that we may not have on the real box, like not having null characters. Technically, because we're sending over a socket, we would be able to send a null character, in this case to that web server, if we send directly over socket versus reading from a file, or reading from a file by catting it. So we'll just real quickly do host is equal to 127.0.0.1. Port is equal to 1111. We're going to need the HTTP scaffolding. So if we say method is equal to get, version is equal to HTTP/1.1, I think. Agent is equal to whatever we want. Nice, man. Accept is equal to everything. So then we just need to build a prefix, which will be the spot that goes in front of our request, or our payload. So that's basically just going to be the method plus a space plus a slash. And then we need our suffix, which that's going to be a little more complicated. That's a space after our payload plus a version plus a new line plus our host plus the port. Oh, we're going to need to make that a string. Let's see what comes next. Another new line. And then agent new line. You can figure all this out if you just look at example HTTP requests or looked at the spec, and I think it finishes off with 2 new lines, or carriage return in new lines. So then we've got our prefix and our suffix. We've got our actual shellcode here. So I think all we have left to do then is to set our padding length, which was 568 if I remember correctly, and our address, which we'll use pack for, literal endian quad word. For now we'll set it to the 6 B's, so 1, 2, 3, 4, 5, 6. The reason we're doing that is we don't know what address we want to use yet. We'll set buff length equal to the length of buffer. And then we can build our payload by doing payload equals prefix plus, we'll do 90 bytes, which is a no-op. Basically just means if we land our instruction pointer there, it'll just continue down it until it hits our payload. And that's known as a no-op sled, or NOP sled. So padding minus our buffer length. So we want enough so that these buffer bytes, which is 74 bytes, and our 90s equals our padding length, which is 568. We're going to have our buffer, then we're going to have our address, then we're going to have our suffix. So that should be all we need there. Now we just need a way to deliver it, so we do socket.socket, socket.af inet, and socket.sockstream, sock.connect, host port, and sock.send payload. So this should be everything we need in order to test this out. So we're good here. Let's save it. We'll save it as, let's call it exploit basic.py. And I think we got everything set up and listening here. We did. So we can actually send this straight from here. If we just hit Control B, it should build it and execute it, I think. And I typoed something. Line 12, cannot assign to operator. So that's supposed to be a plus. Let's save that again. Execute. That time it finished. We hit our breakpoint in process. If we look here, we should be able to see, actually this doesn't look correct. So we see our no-ops here. Let's do a single step. Oh, sorry, I didn't do a single step. I did a continue. Let's restart that. Send that again. We're at our breakpoint. Let's do a single step. And so it looks like we didn't actually overwrite our instruction pointer. So if we try and see why, let's do a find 0x 90, 90, 90, 90, 90, 90, 90, 90. So there's a bunch on the heap, and they're in the stack. So we take this address, and we take a look at what's there. Let's look at 512 bytes. Or 512 64-bit chunks, quad words. That address. And so we can see our no-ops here, and then we see what should be the start of our shellcode, but it doesn't look like it is. And so let's pull up side by side. So we start with a 6A. So we look here, here's our 6A, here's a 29, that's our next one. Jump down here, 58, 99, 6A again, 02, 5F, 6A, 01, 5E, over to here, OF, 05, 48, 97, 48, B9, 02, and we have a null byte in our payload, and so it looks like that is what's causing an issue. And so what we need to do here now is figure out what byte sequences are, or what byte values are not going to work here because they're going to terminate our payload. And so like in this case, that null byte, it's either the null byte or the 11 after it, but I think it's the null byte itself is what's causing an issue. And so what we can do to test that real quick is make a quick Python script. Let's make this full screen again. Jump out here, do Python, and we can just do this in the command line. For I in range 1, there's probably a better way to do this. You could probably just Google for a list of byte sequences or byte values. Print x02x format I think this will work. And so that prints out all these different values that it could have, which is from 00 or 01 to FF. So we copy those. And let's paste them in their own window. And then let's reformat them so it's a little more usable. So if we just do Control H, I think it is, and we'll find all new lines, and we'll just replace them with nothing. And then what we can do is start breaking up each line. Oops. Into 16-byte chunks. And again, there's probably better ways to do this, but this should work. And so now if we just quote it out. Let's set this to Python also, just so that it helps us color code. And we can set bad, or we don't know if they're bad yet, chars is equal to so that should be good. And so if we just take this, let's copy it, go back to our basic exploit, paste it in here. Let's actually replace chars with buff. And so what we're doing here, we can just leave, we could comment this out if we wanted to, but we're replacing this with just a list of all the different byte values. So if we save that, let's make sure that we're running over here again. Start 1111, continue. Oops. And then just run this again. And let's see what I screwed up. Oh, unexpected indent. So let's just do this instead. Let's go back here. Take that out. Let's actually take out all these spaces. can just do buff plus equals buff is equal to there. So that should work fine. Copy that, paste it in here, save it, run it. And so now we see that we've broken again. Again, we didn't get a full overwrite, but we can do the same trick. So we can look for our no ops. And we can find them on the stack, which should be in the same location each time. So if I just actually stick this somewhere useful for now. And then we can examine that spot in memory again. So x, let's do 500 xg. And so if we scroll up to the top, we see our no ops sled again. Do the same thing where I'll split this window so we can follow it easier. Although actually we don't need to follow it this time because we did it in order. So here's the end of our no ops sled. We have 1, 2, 3, 4, 5, 6, 7, 8. And that's it. Then we're nulls after that. So 9 is a bad character. So what we'll do is we'll create a list of bad characters. For now, we'll just do it up here. So x09 is bad. And so if we pull it out of, actually, yeah, let's just do it that way. So we'll do buff is equal to buff dot replace, and we'll replace /x09 with nothing. Save that, start this again, and we'll run this again, break again. Let's go back to that same memory location since that's probably where our no-op sled will start. Should just be able to use up. And so same thing, no-op sled 1, 2, 3, 4, 5, 6, 7, 8, and we're still not getting anything, so 10's probably bad. So we just take this line, replace this with 10. And we're going to rinse and repeat this. I'm going to go ahead and skip ahead on a couple of these because I already know what the values are that are bad. And rather than having you watch me do each individual one of those all in a row, so you would just continue to do that. OA, OB, OC, and OD are all bad. And then I think our next bad one is a bit further, so we'll save this. Start 1111, continue, run. Look at that memory address. See our no-op sled. We see 1, 2, 3, 4, 5, 6, 7, 8. We see E, which is our next one after D. See F. Then we see 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9, 1, A, B, C, D, E, F. And then that's the last of what we see on there. So the next one would have been 2, 0. So 2, 0 is bad. You get the point at this point, I think. So I'm just going to go ahead and finish these out. And I'll make special note of this next one, which is 25. 25, I think, actually looks like everything should be okay because you don't see these null bytes afterwards. But it's actually not, because if you remember in the URL decode, it decodes URL encoded stuff, which starts with a %. The % is equal to the hex value 25. And so what it does then is it takes that hex value 25 and it and it throws it away, and then it takes the next two values and it converts them into a single byte based on what their ASCII value is. And so that causes issues. So 25 is bad, and then finally 3F is bad. Oops. And technically 00 should be fine, but in this case we'll just add that in there also, which is null. And I don't remember on this box if we'll see it. In this case, since this, sometimes you have problems passing an instruction pointer, especially when it's remote, if it's using some sort of string operation, because it can't contain nulls. In this case, the URL decode function will come in handy if we need to, because it will allow us to pass a %00, which will be decoded into a null byte. And so we'll keep that in mind if we encounter it later. I actually don't remember now. So now we've got all that done, and we should be ready to test this out again. And so if we just, do a start, 111, continue, run this, look at that location. What we should see is all of our nops, all of our values, which I won't bother reading out, and this is what matters to us most, is after these ones we see 42, 42, 42, 42, 42, and then some null bytes. So that means we got all the way to our address, which is what we wanted to do. Everything after the address isn't part of the overflow, it's just part of, it's the suffix here, it's the normal pieces of the HTTP protocol that we need to have in order for this to work. So now we're looking good. We're just going to need to generate a new payload without those bytes that we found that are bad in it. So we open this back up to full screen. We'll open the terminal back up to full screen. We'll go to, oops, I apparently closed the window. That's okay. So we'll quit out of this, and we will generate a new payload. So if we do our same one that we did before, this time let's add bad byte values that we don't want to have. So that's, let's see, 00, 0, 09, 0, 10, or not 0, 10, sorry, 10, 0A, 0B, 0C, 0D, 25, and 3F. Oh, I'm missing 20, I guess. 20 and 3F. So this one might take it a second longer to find. It's probably going to use some sort of XOR encoding, yeah, in order to get a payload that doesn't have those values anywhere in it. So we copy this, come back here, let's replace this all. And then let's go ahead and comment out this part. Again, that's just there for our edification. And let's get rid of this replace, although technically it shouldn't matter because none of those sequences should exist in here. Save that. Let's get running back over here again. So it was gdb tiny.c break process plus 426 start 1111 continue. And now if we run this again, come back here, we're at the breakpoint, do next, and we can see that we control the instruction pointer now. And so that's the hard part. Now all we need to do is figure out where we want to point this instruction pointer to get our execution. Technically there's probably two spots in memory or more, which is our source buffer and our destination buffer that both have our code in it. If we were worried about the URL decoding having happened, so if there were values that we needed decoded in order to work, we would need to make sure that we're pointing at the right buffer. In this case, for what we're doing here, since we made sure we didn't have anything that was bad in our payload, we can just point to anywhere that contains our code. And so we can just do a find and look for our no-op sled again. So 0x9, oops, too many, that's okay. So we look for all of our no-ops, and we just take the first one here at the top of that stack. And so now what we can do is we can use that address, and we'll look at the memory here real quick, x 500xg. So basically what's going to happen is we're going to jump to this address. We're going to slide down our no-op slide, and we're going to hit our shellcode. So we'll replace this value, our instruction pointer value, with the address up here. And so what should happen is we should execute, or we'll get to this spot, we'll jump up top, slide down, hit our code. So if we start 1111, continue, let's fire up a listener over here, nclvnp 4444. Let's go back here. Let's replace this with that value. Save it, run it. So now we're broken. If we do a single step, we see this RIP value change to what we put in, which is the start of our no-ops. If we look at the code here, we've got no-op, no-op, no-op. If I was to do n and just keep stepping down, we're just going to step down our no-op sled. I'll just hit continue so that we run. You'll notice it says process blah 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 is executing new program user bin dash. If we come back here, we've got a connection. If we do ls, we can see what's in the directory we're in. So we know now that this works at least on our local box. What we'll do first is adjust it on our local box for the real tiny, because it's possible, because of those lines for the multi-threading that we commented out, that we're going to have some slightly different values. So we'll want to make sure that it works against the real tiny locally, and then finally we'll point it at the tiny on the remote system. So close out of that. Let's start this back up. Let's quit here. Let's do GDB tiny smasher. Let's see, we're going to need to disassemble our process again. Disassemble process. Reason for that is you're going to see that the instructions have changed because of the way that, actually, now that I think about it, I actually thought about that before. These instructions shouldn't really be changing. The instructions in main should be changing. So it's possible that other things were changed on the version, because we didn't grab the code from the server itself, we grabbed the code from the GitHub repository. So it's possible there's some changes. For now, we won't worry about that. We'll just do a break. And we'll break at process plus, it looks like we've got to return at 210 and we've got to return at 221. So we'll break at return at 210, 221. And then we'll do a start 1111. Do a continue. And so it looks like we're good. It's giving us a warning here that source file is more recent than the executable because it's trying to match the tiny that we're running against the tiny.c that we downloaded. We can ignore that. And so now, if we just run this again, come back here, looks like we didn't actually hit a breakpoint yet. Oh, we're at the breakpoint. Okay. So, looks like we had some issues. We did overwrite RIP to the value that we wanted, I think, CCF1. Yeah. So likely our address is different, so we do find, we try and find that no-op sled again. Top of the stack, so yeah, our addresses are slightly different, which is no problem. We take that one, paste that into there, save it, start this thing back up again. let's try to send it and see what happens. So this time we didn't hit a breakpoint, probably because we're in some thread that's not the main thread, but we did get a connection. And we can check, or we can run ls, we can run commands, who am I? So that works. So let's go ahead and start this up again, and what we'll do is we will fire it at the real system. So let's replace this address with 10, 10, 10, 89, save it, and execute it. And then come back and see if we got a connection. We didn't. Execute it a few more times just to be sure. Nothing. And so as I thought, it's not that simple. It's highly likely that randomization's turned on, in which case those addresses that we're putting in aren't pointing to the correct place. So we're going to have to go with a slightly more complicated technique, which we will do here in just a second. So what we're going to need to do now, instead of our traditional technique that we just tried, because of the fact that ASLR is likely on the remote system, we're going to have to try something slightly more complicated, which will be a return to libc attack, or ret to libc. Basically what we're going to do is we're going to try to see if we can assemble some instructions that will get us remote code execution using nothing but what we find in the executable and in shared libraries. This is fairly simple to do when you're running everything locally. Because we won't be able to actually run the code locally, we'll have to get the server on Smasher to actually leak back an address to us that we can use to start calculating where other functions inside of libc would be. And so why don't we just go ahead and get started. What we'll do is we'll build up a Python script. We'll save this exploit basic as, let's just save it as straight exploit. Oh, sorry. Save as. Save it as exploit. Oh, that's interesting. There shouldn't have been one in there already, but I probably had something from another system that synced up. So now we've got our code we were using before. The only reason we're just saving that is because we can reuse some pieces of it. All of this shellcode isn't usable for us anymore. Our padding length is still usable. Address is usable. This payload construction isn't really that usable. Buffer length we'll get rid of. So we'll still have our code to send the payload to the server. We'll still have all of our code for setting up HTTP request. And we'll padding length. Let's actually just get rid of this generic address for right now. So we're actually going to have to build this as two stages, because our first stage we're going to be trying to get the leaked address back. The second stage we'll try and actually build a sequence of instructions to get us some sort of reverse shell. Hopefully we don't run into any big problems here, since I didn't plan this out super well. One thing we are going to need to do, so let me open that other one back up again. Exploit basic is make sure that these bad characters, which I think are at the end of here, that we're filtering these out, because since we're not going to be generating a payload ourselves, we're no longer going to be able to control what characters are in the payload that we send. So let's just paste that up here, comment it out. And let's create a quick function that will allow us to sanitize our payload. So we'll call it sanitize payload, I guess. Pass in a payload. And so we'll do bad bytes is equal to, and we'll create a list here. So we don't want null byte, we don't want 9. We don't want AA, we don't want AB, don't want C, don't want D, don't want 10, don't want 20, don't want 25, and we don't want 3F. So that should be good. You can have a string here, output payload. We'll set it to blank initially, and then we'll do a for index or IDX in range length of our payload. If the ordinal value of payload at IDX is in bad bytes, then let's replace it with a URL encoding. So output payload plus equals, we'll use a format string here, 02x, format the ordinal value of payload at index. So that should be good. Else output payload plus equals payload at IDX. So this basically will just encode any of these bytes that are found with URL encoding and append them to our string, and then at the end of course we return output payload. So that should be good enough to sanitize our input. And then let's create a stage 1 here. This will be our first stage, which we can build separately. Let's actually change this IP address back to our local host so that we can debug it as we go. And so stage 1, we're going to need a couple things. The way this works, and I don't want to go into too much depth on it just because of how long it could take to cover things thoroughly. Hopefully you know enough about it. If you don't, research rect2libc, research PLTs, which are procedure linkage tables, and GOTs, which is a global offset table. But basically, the PLT address shouldn't change. It should always be the same, assuming that pi isn't on, which it isn't in this case. And so that should point to the global offset table. The global offset table is going to get the address of whatever the function is that we're trying to call in libc. At runtime, it'll be dynamically linked. So the first call to it won't be populated. It'll go back to the PLT. Then it'll get populated, or it'll get populated anyway. So basically the PLT will end up pointing to the actual address of the function in libc as, or inside of that running process. So basically we need the PLT address of some function. It'll be right in this case. We're gonna have to pack it. So again, little endian quad word. We don't know what it is yet. We're going to need the GOT write address, which is what we're going to leak. So PLT write's what we're going to call, GOT write's what we're going to leak. Again, it's going to be a quad word in little endian. And that's all we know so far. So what we need to do now is, let's kill out of this. We need to find where the PLT address is of write in libc. So if we just do object dump -d tiny smasher, we'll grep for write. And so we see up here this write to libc. This has everything we need in it. It has both the GOT and the PLT address, which this is the PLT, this is the GOT. So if we take that, we'll add that in here just as a comment. And again, this is for my local system, which this shouldn't really change unless there's big differences in the OS. So like, we'll probably have to rerun these inside of a VM that's running Ubuntu 16.04 or whatever the system was running, because it's probably going to be different between this Kali box and that. So we've got our PLT and our GOT write. Now what we need to do is find gadgets that will allow us to get these to where they need to go. So in 32-bit systems, again, I'm just going to do a really fast coverage of this because there's not time to dig in deep. 32-bit systems, all these arguments would be passed on the stack. But because of the fact that we are running on 64-bit, they're not passed in the stack, they're passed in registers instead. And so they're passed in RDI, RSI, RDX, and RC. Actually, I don't remember what the fourth one is for some reason. But anyway, basically what we're going to need to do is we're going to need to populate RDI and RSI, because write has two arguments to it. And so we'll have to populate those two arguments before we call it. Actually, I take that back. As I said that doesn't sound right. So write has three arguments, I think. It has, let's look it up real quick. It has a length argument also, I believe. So if we look up write, probably let's see. Or just do write like this. There we go. Yeah, so it takes a file descriptor, takes a buffer, and it takes a count. And so this would be in RDI, this would be in RSI, and this would be in RDX. And so this is probably going to be a little tricky because of the fact that there's not a lot of instructions that pop something into RDX. But we'll see what we can find. I think I found something previously when I did it that we could make work. So we can do that with a number of tools. We could do it inside of GDB, I think, with PETA. Instead, I think I've got Roper installed on here. I do. So we can do it with Roper. So if we just do Roper file tiny smasher search, and we'll search for RDI first. Doesn't really matter. Let's see, what we're going to look for is something like this, a pop RDI return. And so this will pop the value on the top of the stack into RDI, and then it'll return. So if we just take this address, and we'll make a comment for it, pop RDI and ret. And then we need to find a pop RSI. So if we go back in here, do the same command, but this time look for RSI. And so here it's a little trickier. We don't have a pop RSI in ret. We have a pop RSI pop R15 in ret and a pop RSI R15 RBP in ret. This one should work just fine for us. I'll show you what we'll do to get around the fact that it's popping an additional value that we don't care about off of the register, or sorry, off of the stack. So this was a pop RSI R15 and ret. And then we need a way to set RDI, or sorry, RDX. So RDX. And here I don't see anything that's going to work for us necessarily. So since we don't have something here that's going to work, what we're going to need to do is be a little bit trickier. And the way you would figure this out normally would be to just Google for ways to set RDX. But I happen to know that string compare sets RDX. And so basically, I forget what exactly it sets it to. I think it's set to the difference between the two strings that it's passed. So the numeric difference, like if one's 5 long and one's 10 long, it's set to 5. So what we can do is we can see if we can find the PLT address of string compare, and then we can call a string compare, which takes 2 arguments, and we can pass it a couple random spots in memory, like its own address, the address of the PLT for string compare, and then the address of the PLT for string compare minus 8 bytes or something like that. And that should get us a big enough value into RDX that this works. And what's going to happen there then is when we call our write, let's say we call our write with like 15, and we're obviously only passing back 8 bytes, or 8 bytes we care about. So we'll end up getting 15 bytes back, so we'll actually get a buffer overrun back, so we'll get some sort of memory leak, which we don't care about in this case. We'll just chop off the front 8 bytes. We'll take that. That's our address for the write function in libc. So we need to repeat our instruction up here where we grep for write. This time we need to grep for string compare. And so we have that here. So we'll take that. And we'll paste that over here for now. Again, comment it out. So we're going to need a PLT for string compare. Oops. String compare. And that's going to be equal to pack. Quad word, and this 0x at the front, and then we're going to need our 2 addresses, so we'll call them like string compare val1 and val2. It's going to be equal to pack little endian quad word. We'll just use that same address, and then we'll do string compare val2, oops, and that's going to be equal to pack, and we'll do the same address again, but this time we'll take like 8 away from it or something. Basically what it'll do is the string compare is going to run from both of those addresses, run up until it hits nulls, and it's going to consider that the length of the string. We may have to mess with that a little bit locally to make sure that the number is big enough to return our address, but it should probably work. And then let me think of what else we're going to need. So if we look back here at write, it takes a file descriptor, so we're going to need that. A buffer, we don't need to worry about that because we're passing that. The count, again, we're okay there. So the file descriptor is going to be something we need. Luckily, if you noticed when we were running this before, the file descriptor generally for the listener is 3. The file descriptor for the requests when they're accepted is 4. It could technically be something else, so we may need to build to brute force, but for now we're going to go ahead and hard code in 4 as the file descriptor. And again, we can just kind of tweak this locally as we need to. So if we do fd is equal to pack, little endian quad word, 4. And then finally we're going to need some sort of an address to return back to. And the reason for this is because we don't want to crash. If we crash, the executable loads again, then it's going to randomize again. And so basically, if we run this first part, we successfully leak the address, we crash, we try and run the second part, well, now that it's crashed, it's probably going to have randomized addresses again. And so it's easier if we can just jump back to somewhere that works, somewhere that will allow the code to continue executing, which in this case will make the start of main probably. So if I go back here and do gdb tiny smasher, and we'll do a disassemble main. And what we'll look for here is the start of main. So this address right here, 60, 6 bytes should be enough. And so we'll replace that with the address of entry into main. This could possibly cause an issue, which we'll see in a second, where when we jump back here, it may start listening again, but on the default port, since we haven't passed anything in as the arguments. And so in that case, we may need to build our second phase so that we connect to a different port, but we'll cross that bridge when we get to it. I think that was an issue I encountered in the first one, which we could deal with, but it's just not worth it. It's easy enough to just change the port for the second connect attempt since they're separate connections anyway. So I think we have most of what we need. Oh, other than we've got to actually build these things out also. So We're going to need, well here, let's create a junk value for R15, because remember we've got to pop something into R15. Doesn't matter what it is, we don't care. As long as it's a little endian quad word, we'll make it set to just B's. So there's 1B, 2B, 3, 4, 5, 6. And then we're going to need our pop RDI instruction, which is going to be equal to pack quad word and 2, 3, 4, 5, 6. Oops. Probably clean this up so it looked a little bit nicer. And then we need a pop RSI and R15. Again, you can name these things whatever you want. I like to use descriptive names because it helps me remember what exactly things are doing. If I just called these like X, Y, and Z, it might be a little bit harder to follow along for me, especially later on, like if I review this stuff down the road. If things aren't very descriptive, it takes a while to figure out what exactly it was trying to do. So I think we have enough to build our first stage now. So what we'll do is we'll build payload. So payload is equal to some empty string. And then payload is equal to A's times our padding. And so that gets us our initial padding. And then we're going to want to start building our different instructions. And so what we'll do is I'll try and put these all on lines where they make logical sense. So like this line is going to be our call to string compare, and it's going to be passing in those two values. So we'll do a pop RDI plus string compare val1 plus pop RSI R15. And so basically what we're doing here is we're popping the value of this first string compare address into RDI, popping the second value into RSI, and then putting some junk in R15. By the way, I apologize if I can't talk very well while I'm doing this. Sometimes it takes a little more thought than some of the other stuff. And then finally our PLT string compare address. And so we'll say that this is populate RDI and RSI and call string compare to get RDX set to a non-zero value. And payload is equal to, and this will be where we call write with the address, the GOT address of write. So we'll need to pop RDI again with our file descriptor, pop RSI and R15 with our GOT write address, plus R15, which is our dummy value, plus PLT write. Just to answer the question before it comes up, let me finish typing this out. Populate RDI and RSI with leaked address and call write. So some people may be thinking that what we're sending is this GOT write, this address, and it's not actually. What we're going to do is pull out the value that's at this address, which is going to be the real write address. And that's what we're going to be sending back. So we're not sending this back, we're sending the value at this location in memory, just so that we're clear on that. And then what we need to do is pop back to our main function in this case. We'll just payload, oh, you know what, I forgot plus equals on all these last. This way. Okay. So that should be the end of phase one. Remember I said that we've got to sanitize, so we'll set payload equal to sanitize payload. So at this point we should have our sanitized payload and be all ready to go. We need to build our request. Stage 1 request. And that's going to be request is equal to prefix plus payload plus suffix. And that is all there is to that. Let's actually take this just to clean the code up a bit. Create a second function called send, def send, request. Take this, take that. So that should be good enough. So now we can just send request, and so that should send our stage 1 request. And then of course we will need to receive on it. So if we do response equals, you know what, this is going to actually make it harder having it in here. Let's just keep it where it was. So if you were making something that's reusable, you'd want to start popping things into functions and make the code a little cleaner, but in this case it's probably not worth the time that it would take. So after we send the request, we're going to read from the socket. And actually, we're going to need to read twice, but because we don't want to read, let me think real quick. So it's going to be a little bit trickier. I think I have, let me look outside the screen here. Yes, I do. Okay. So remember how we get back these responses from the server? Well, in this case, there's something here, but if we were to call something that didn't exist, this file not found response, we need to grab this first. And actually, so this is 94 bytes. So what we'll do is we'll do a receive of 94 bytes. And we'll just throw those away. Throw away. Not found response. Response is equal to sock.receive, and we'll receive 1024 bytes. This should have our right address at the front, and then the rest, some odd number of bytes, is going to be junk. And so then we will set our live write equal to unpack literal ending quad word from response, and we only want the first 8 bytes. And then this returns a tuple, I believe, so we only want the first element in the tuple. And so then if we do a print live libc write address, and we'll format it nice and pretty. Oops. Format live write, and then we will do a sock.close, and we'll do a raw input just so that we hang here. Well, actually, we don't need to. So we save that. This should be good enough to get us the live libc write address. So we can try this out locally real quick. So we have, let me make sure this is the right executable. Yeah, we have Tiny Smasher loaded up already. So let's actually disassemble process again real quick. Let's set a breakpoint, break process plus 210. I think that's the one we broke on last time, so we don't need to set anything at the second one. Do a start 1111, do a continue. And then if we run this, and it looks like I probably have a problem somewhere. Integer out of range 4Q format, line 41. Oh, 0x. And I messed something up here. key is not oh, typoed that. File descriptor. And so it looks like it sent it. It should be sitting at our breakpoint. It's not sitting at our breakpoint. Oh, because this is multi-threaded, so it's possible that it didn't hit the breakpoint and that we got stuck somewhere else. So we are sending this to localhost. There we go. So I don't know why I didn't run that time. So it claims that liblibc is at this address, which ends in 9290. We should be able to verify that by doing a break on that, and then info xi and that address. No, 0x. And so we can see that that is the address to libc, right? So we did leak back a good address. Now we can see we can actually execute that on the remote server. And 10.10.89 and run it. And so it was able to return an address. Actually, it looks like it might be the same address. No, it's not. Okay, so we know that that works. Let's turn back to our local address. And let's build our second stage. And this is going to be a little bit more complicated. So we finish here. This live write value is populated, so we're good to go for stage 2. And actually, let me see if we can see it in here. Oh, we probably can't because, oh, we can see it over here. So, oh, do I have 2 GDBs open? That could have been why I was having weird issues. So we can see that we're listening on port 999 all of a sudden with file descriptor 5. So that means that we did jump back to the main function and start over again. So we didn't exit out, which is good. So all of our addresses should be staying the same. But we'll have to keep, excuse me, we'll have to keep that in mind when we build our second stage. So actually, let's pop this up. First thing we can do, so we don't forget that, is reset the port to 9999. And so now what we're going to need to do is find what the base offsets are for a bunch of the functions that we're going to need to use. We can get those hard-coded. We can then perform some calculations to figure out where they actually are in memory. The things that we're going to need are going to be right, which we already know. We're going to need to find a gadget for system, or sorry, not a gadget. We're going to need to find where system is. So let's quit out of both of these instances of GDB. So what we'll want to essentially try and do is, actually I'll put it up here, I guess. We're going to try and call system with bin bash or bin sh is the argument, so that we spawn a system call. Now the trick to this, as you may notice, is that if we were to even get this to execute, that it would simply call system in the remote process and we wouldn't have any way to interact with it. So in addition to this, let's see, we're going to need to duplicate our standard in, standard out, and standard air file descriptors, and then call this. And so what that'll do is it'll duplicate standard in, out, and air to our sockets file descriptor, and then we'll call this, and that will actually allow us to interact with it. Again, we're going to have to guess the file descriptor And again, it should be pretty easy to guess, even on the live system. It's possible on the free ones, if there's a bunch of people interacting, that the file descriptors get incremented up more, but on these ones, I haven't seen it get incremented much or at all. So basically, as we saw before, when it restarted, jumped back to the top of main, started listening on 9999, it was file descriptor 5 because that was the next available one. That means when it accepts a connection, 6 is going to be the one that it accepts it on. So we can also assume that FD is equal to pack Lindian quad word 6. So that'll likely be our file descriptor. And so for this one, we're going to need a couple things. We're going to need libc's write base, which is the offset. We'll set that to nothing for now. We're going to need libc's system base. Oh, thanks. Sublime Text went ahead and tried to autocomplete that one for me. We're going to need libc's dupe2 base. Which again, let's take a real fast look at dupe2 man dupe2. And so dupe2 just simply takes the old file descriptor and the new file descriptor. And so we should be able to use that, pass in 1, 2, and 3, or sorry, 0, 1, and 2, and then our network file descriptor, and that should allow us, to duplicate those over. So we're going to need the address for that. And then finally, we're going to need libc's bin.sh base. And what this is, as you'll see in a second, is inside of libc, there's already the string /bin//sh, which is what we're going to use as a parameter to system. So let's go ahead and see if we can fill in some of these values. I'll split these windows so that we can work like that. So if we do a readelf -s libc.so.6, oh, I need to find libc first. Locate libc.so.6. And again, we might need to adjust this for the values on the live system. So this is the one we want. We'll just copy it to our local working directory to make life a little easier. Since we have remote access, or access to the remote system, its file system through that web server, we can copy that one once we've made sure this is all working. That way we know we're working with the same version. Otherwise the offsets and stuff could be slightly different. So now we want to do readelf -s libc so6 grep write, and we're going to want to look for write at Ghibli, this one right here. So we'll copy that. I think that's the right one, yes. So we'll paste that there. All these leading zeros technically don't need to be there, but I'll leave them in since it's easier in this case. We'll do the same thing, but this time for system. Again, there's our call, or our address. And we'll do it for dupe2. And then to find our string, we're actually going to do that a little bit differently. So we're going to do strings -a-tx libc grep bin.sh. And there's our offset for that. And then we can create some values here that call it system distance, or dist, libc write base minus libc system base, dupe2 distance, libc write base minus libc dupe2 base, and bin sh dist is equal to libc right base minus libc bin sh base, and there's a million different ways you could do this. And so we'll want to create a system value, which will be equal to pack little endian quad word live write minus system dist. And then dupe2 is going to be equal to pack quad word live write minus dupe2 dist. And bin sh is going to be equal to pack quad word live write minus bin sh distance. And then we're going to need our standard in, out, and air. So std in is equal to pack endian quad word 0, 0. Std out is equal to pack 0, 1. Std air is equal to pack 0x 02. Okay, and now we're going to need to craft our payload. So payload is equal to nothing. Payload plus equals, we'll use a different character this time. We'll use C times, what was I calling it? Pad length? Padding. And then we're going to want to call our duplicate functions. So payload plus equals, and so remember dupe2 is going to take the socket and the standard in. So like, here, let's look it up, man dupe2. So it's going to take the socket as the old file descriptor and the standard in, standard out, and standard air file descriptors as the new one. So if we quit out of that, and so those are going to be passed in RDI and RSI again, so we can reuse our stuff up above, our gadgets for popping RSI and RDI. So we set this equal to pop RDI plus file descriptor plus pop RSI R15 plus, we'll do standard in first, plus R15, which is our dummy value, plus dupe2, plus dupe2, and we'll call this call dupe2 socket standard in, payload, actually let's just copy this line because it's almost the same. And so we'll do standard in, standard out, and standard air. So that should duplicate all three of those. And then we're just going to want to call system with that bin sh. So payload plus equals pop RDI plus bin sh, which will be our argument that's going to system, plus system. And that should be it for that one. Call system bin sh. And then we'll do payload plus equals last to send it back to the main again. We'll sanitize it. Payload is equal to sanitize payload. And that should be good enough. We'll print out all the values of these different things we've calculated just to make sure that we can check them in case we need to debug, which we likely will. Libc write, write 0:016x format live write. Just copy and paste this. So So we have also got system, dupe2, and bin.sh, so we want to look at, so, oops, C system, dupe2, bin.sh, and the values we're going to pass to those are packed already, so we'll need to unpack them, unpack system, dupe2, and bin.sh. So we've got all that. Let me make this full screen again so that you're not looking at it in partial view. And so now we just need to build our request again. So request is equal to prefix plus our plus our payload plus suffix. So let's take our sending code from up top, wherever it's at, right here. Actually, before we send it, let's put a raw input. Press enter to continue. This will allow us to kind of check things before we actually send the payload. And then I suppose we need to build some sort of way to interact with this. Again, I'm not going to put a ton of work into it because we're just going to try and use this to kick off some type of, a normal reverse shell or something else, rather than working through a web-based shell or whatever you want to call it. So we'll do a receive. This will be our file not found message, which is why we're calling it junk. And then we'll do a while true. CMD is equal to raw input. And we'll just prefix it with a hashtag. Sock.send. CMD plus a new line, and then we'll do print sent format command, and then we'll do response is equal to sock.receive 1024. Oh, let's make it bigger just in case. 2048. Print, oops, response, format response, and that should be good. And then we'll do a sock.close outside of that while true, which will never actually be hit, but that's okay. So I think we have everything we need here. We've got it set to go to our local host. So let's get one of these fired up again. GDB tiny smasher. Start 1111. Continue. And then let's execute this. So here's our live libc write address, which actually I think we still have ASLR turned off, so we should turn it back on just so we can prove that it works with ASLR enabled, but for now I think it looks like it's the same address we got before. So our libc write address is obviously the same as that. libc system address is still the same as that, so something's wrong there. libc dupe2 address is still the same as that. Did I copy and paste and not change something? No. It's interesting. Our libc bin.sh address looks like it's different, but these other ones... Oh, there is a typo there. I have the base is the exact same address. So that would explain that. Let me get those addresses again real quick. See which window they were in. find them again. So if we do read elf s libc so grep system, so that's the address of system, and do 2. It's fun when you make mistakes because then everybody can see what you would do when you screw it up. And so now we have different addresses for all of those. So try running it again. And so now we can see all the different addresses. Let's see if these addresses are actually correct. So I copy this address and I look at what, let's see, break it, what instruction is at that address. Can't access memory there. Oh, I didn't copy it. So that is libc system. So it looks like we're calculating those addresses correctly. So if we hit enter here, we should see, well actually I'm gonna have to restart it now because I errored it out of here, but start, continue. So if we run this again now, I might have screwed something up by interrupting it. Okay, press enter to continue. Looks like we have FD6, so we did spawn a listener on 9999. We did accept a request on FD6, but now we're just kind of blocked here. So presumably something wasn't quite right. And so we're going to need to figure out what went wrong there. So I think we should be able to use our single-threaded version of this, which will be easier to debug. Don't think that there should be any fundamental changes with this attack between the two. We do start 1111, do a break at process plus 426, I think it was. Oh, sorry. At the address of process plus 426. And do a continue. Our address is already in use. So we need to kill off, let's do this. There was a kill script they already had in here. So we'll just borrow that. That should be the only line we need. Oops. Apparently I'm having problems copying and pasting today. Let's echo that into kill and chmod plus x kill. I think that worked. Cat kill. Yeah. Oh, no, it didn't quite work. Then kill. So it looks like we're missing just a piece of it, $2. Okay, so back to our debugger. Break at process plus 427, or sorry, 426. Start 1111. Continue. So now it's listening. And then we'll just run that. And we're broken. This is the initial, this is our stage 1 payload, as you can see. So we'll just continue past this. And we get a sig kill. Looks like we didn't have a right address, so it's possible there is a difference between these two. Start 1111. continue. So let's try this again. Let's make this full screen. So we're broken at process. Let's see if we look here. Let's do one step. So yeah, it looks like we have some bad addresses. So it isn't actually the same between the two. That's okay, let's quit out of this and try and go back to the original one then, smasher. And start 1111, continue. Execute that, enter. So it did accept it. Let's take a look and see what may have gone wrong. Let's check those addresses that we're getting. So let's see. So we do print write. So write is at 9290, which matches up with what we had. Print system. System's at 35D0, which is what we have. Print dupe2. Dupe2 is at 9AF0, which is what we have. Actually, we should look at the whole thing because this bit me before. System is at 7E335D0. 7E335D0. Dupe2 is at 7ED9AF0. 7ED9AF0. Yeah, so those are good. And I think it's search. I don't actually remember how to look for strings in here. Bin sh, find, bin sh. And so that's at 6F. Yeah, so that one looks right. So all of our addresses are correct and should work. Scrolling up, it looks like our file descriptor was correct. So, since everything looks correct, let's quit out of here, start it up again, start 1111, break at process plus 210, and then let's make sure we have set detach on fork to off, that way it should follow children. And then continue. Oops, what did I screw up there? Oh, oops. I pasted something in there somehow. Save that. And so we hit our first breakpoint. This is for our initial leaking of the libc address. And that looks okay. So we've got string compare, which this is setting our RDX value. So that all looks okay. File descriptor is 4 here. And as we've seen, that part seems to be functioning, so we just continue. We leak it back, we get all this stuff, we accept a request. So at this point we should have another request. When I hit enter here, we should actually send it. Let's take a look real quick and just make sure I didn't screw anything up there. So send request, our request is equal to our prefix plus our payload plus our suffix. And this is our payload. So that should all be correct. So I hit enter. And we can see we didn't hit our breakpoint again. It's possible because we restarted that we didn't attach to it though. There's a lot of weirdness when you start getting into these strange loops where you're jumping back. And so, problem is it's a little more difficult to troubleshoot what's going on here then. So let's try and do this a different way. We'll kill out of this. We'll start up Tiny Smasher locally without the debugger attached to it. So Tiny Smasher 1111. We will run this code. Take this PID. that's attached to it now. So gdb -p. So it looks like we are currently in a glibc or a libc read. We haven't actually sent our payload yet, so we should be able to process or disassemble process. We should be able to block on that same return, so break at process plus 210. Let's break at that second one just in case, also 221. So now we should be able to continue. Now if we hit enter in here, you know what, I'm actually going to try and run this locally instead of in Sublime Text, because I'm not positive that Sublime Text isn't what's screwing this up. So let's kill and start this again. We can use the same technique, but let's just run it without Sublime Text. We open another window, Python exploit.py. And so we look back here. This is our PID for that secondary connection. So do gdb-p PID break at process plus 210 and 221. Continue. Hit enter there. Now we've got a command prompt, so that's a little different than what we saw before. Although it is interesting, we dropped back to our debug shell or debug prompt here. So we can see everything's filled with our C's from our second payload. Our 15 is filled with that bogus, the all B's that we set. Our IP is pointing to process at 210. So we should be, oh, that's why, okay, we're broken at the point where I set the breakpoint. So if we look here at our stack, it looks like we've got the value 6, but it looks like it's being, okay, yeah, okay. Pop RDI, so we're popping 6 into RDI. We're popping 0 into RSI, so this is doing our dupe 2, and then we're popping this junk B's into R15. So let's just do next to step over these. And then we've got our call to libc with binsh, or sorry, not libc, to system, binsh. So we just continue from there. We see user bin dash, bunch of junk, new process, user bin dash. So if we switch back here and see if we can execute a command, ls works, who am I? I'm root. Again, this is obviously my local system. So now what we need to do is see if we can actually get this to work against the real system. I'm guessing we'll have to adjust our offsets, but that's probably it. So let's kill out of that. Let's detach and let's kill this. Clear everything up. And so let's grab libc from this system first and foremost, which is in lib, let's see, locate libc.so.6, user lib x86-64. Like it's in any particular order. So what is it? It's x86_64 Linux. xgnu. And then libc.so.6, file not found. Interesting. Find libc.so. Possible it's somewhere different on this system. Let's try this. Let's see if it's in here. libc.so.6. There it is. So we'll just save that. Sorry, voice has gone away. Let's copy the link location. wget. And so now that we've got that, we can go back and look for those addresses. Split the window again. So we'll do a... oh, did I download it? That's fine. So if I do read elf s libc so.6.1, grep write. So this is the base address overwrite. Which, as you can see, is different. Write system, which is also, also different, slightly. We had forgotten to enable ASLR on our local system too, so I could have shown you how this would work even if ASLR is on, but we'll see that on the real system whether or not it's on. Since I don't want to waste any of your time going back and doing that again, dupe 2. Making sure that I actually copy the right addresses this time. And then strings atx libc so61 grep bin sh. So that also is in a different place. And so I think the rest of this should be fairly universal. Yeah, the rest of this shouldn't matter. So we save. Minimize that out of the way. We'll do it the same way as before, where we don't execute it inside of there, since I think that was just an issue I was seeing with that. Need to change the IP address. 10.10.10.89. Save again. Minimize that. Python exploit.py. So we get back all of our addresses. Let's save this so we can actually test and see if ASLR is on. One of these other windows, we'll just stick it somewhere. We can actually just cancel out of this, do it again. It's definitely on. So as you can see, the address here changed between the two runs. So now that we've confirmed ASLR is definitely on, this should work anyway, but that explains why the first one didn't work. So let's just see what happens when we hit enter. We get a prompt, send ls, and we get back index.html. So it looks like we are good to go. Who am I? I'm dub. So since we have a shell now, and if you remember from the Nmap scan originally, we saw SSH was open. What we can do is we can just generate a public-private key pair, stick it in the right place, and we should be able to SSH in as dub then without compromising other users' ability to do this box. Like they wouldn't be able to shortcut and get into SSH because they would require our private SSH key. And so that should be a good way to do it. There's obviously other ways we could get a normal reverse shell. There's, Pentest Monkey has tons and tons and tons of different ways we could do it. But the cleanest way, I think, is to just get a good old SSH session. So we do SSH keygen, and we'll call the key smasher www, and we won't worry about creating a passphrase on it. So we cat smasher www.pub, and we take this, well, we don't need the end part, copy that, and we do a echo to .ssh authorized keys. We might need to actually create that directory. Yeah, so we need to mkdir /home www.ssh. And it looks like we may have an issue with our shell. Let's just try and kill it. Exploit it again. ls-la, the home directory. So .ssh did get created. So now if we try it, echo this to .ssh authorized keys. And this is why we want to get a better shell. This thing keeps having heart attacks. Cancel out of it again. Exploit it again. Cat. Let's see if we got our key written in. Authorized keys. Looks like we did. And so we should be good to log in. I think we need to chmod -r geo equals .ssh chmod 600 .ssh authorized keys. Let's exploit it again and check and make sure our permissions look good. ls-la .ssh. It should be good, I think. So now over here, if we do ssh -i smash www www at 10.10.10.89, and we're logged in as smasher through SSH. And so as you can see, the screen looks a little bit different now. I had actually paused that video, went to eat lunch, came back, and continued on when I realized that yet again my mic was muted. And so I had gotten about 18 minutes into this part of it when I realized that rather than completely wipe everything out and start all over, I figured a lot of these steps are stuff you've seen in enough of my videos that rather than redo them from scratch, I'll just kind of walk through them again really quick. So basically, once we were logged in, created a directory in a temporary place, we did a wget to pull down linenum from our local system. We ran it with -t, which makes it run thorough tests. We saw all the default stuff here that we had already seen before. And the couple interesting things we saw in here were in our setuid stuff, or actually I guess before that, we saw a local listener on 1337 that wasn't being exposed externally. And when we looked at the processes, we can see that that's probably this SOCAT here. And actually, yeah, so we can actually see it right here when we look at, so it's running some crackme.py, listening on 1337, bound to localhost only. And so that was one of the interesting things we saw. The second interesting thing we saw was in the SUID files. We noticed that there is one here that's fairly new, a lot newer than the other ones, which is called checker, and it's also not something that we typically see. So we had checker and we had that that socket that was listening. So we ran a Python web server here locally. We pulled down checker to our local box. I don't know where I put it here somewhere, so that we can look at it later. Although basically when I ran checker, let's see, we should see it here somewhere. Yeah, right here. You are not Smasher user, please level up, bro. And so basically it's doing a UID check. We're not the right UID, and so it's not letting us run. So this is likely a component that's used further on. So we grabbed that, and then we made a connection using netcat to that local port 1337. We get a welcome to AES checker. We're getting asked to crack this one. If we insert some garbage, it gives a generic error, more garbage, another generic error. Put in the value that gives us to crack, gives us hash OK. We insert that with some stuff modified, we get generic error. I modify just one of the bytes here at the end instead of the base64 padding, and we get an invalid padding. So what that told me was that this is a padding oracle attack. If you're not familiar with those, you may not have known what it was. Essentially, it's a way to use a service that decrypts some encrypted blob to tell us whether or not we're modifying the right values, so that we can essentially decrypt based on the responses we get from this padding oracle. And I'm not going to explain it here because A, I would do a horrible job, and B, there's some great stuff online which I will include links to in the description that explain it really well. But basically your blocks need to be padded so that they're the correct length. So if it's 16 byte blocks and you had 13 bytes of data, you would need to pad with 3 bytes, and those 3 bytes would all be set to 3. If you needed to pad with 4 bytes, they'd be set to 4, 5 bytes, 5. You get the picture, hopefully. And so because of that, you can tweak the rightmost bytes and send them back to the padding oracle, and you can basically use that as a way to start figuring out what the plain text values are by tweaking those, since each block is XORed with the previous block, and basically you can use some math to be able to reverse back to what the plain text input was given the responses that you get from the padding oracle. There's a nice Python script that's already made to do this. We pulled it down from here, from this GitHub site. They have an example. Their example's made to work with a web service. We're not using a web service, so we've got to modify it a bit. We also needed to be able to access it, and so since it's using Python libraries, we have the choice of pulling the libraries with us, packaging the executable with everything in it, or doing it remotely. Packaging it or pulling the libraries is probably the best way to do it, but in order to save time, I just did it the way that I originally did it, which is by opening an SSH tunnel, which is what we see here. So SSH-L, I'm forwarding port 1337 on my local host to 1337 on Smasher. The error that you get here, the problem that you have with this, has to do with the way that network-based reads and writes are done. And if you're not familiar with that, if I write data to a network socket, there's no guarantee that the read on the other side is going to read every single byte of data that I wrote. It may read more, it may read less. More being if I wrote, let's say I'd make 2 writes, it may read those 2 writes as one single read. It may read 1.5 of them. It may read only half. There's no guarantee to what the size of the reads are going to be, despite the fact that we ask for 1024 byte buffer or whatever. And so because of that, it caused issues with the padding oracle, and so I had a bunch of problems where the padding oracle would bail out, look like it was done, but the blob that I was left with was nonsensical. I couldn't figure out what to do with it. Eventually I figured out that the blob I was left with changed each time I ran it, which wouldn't happen if the padding oracle attack was working properly. So I ended up throwing a sleep in there. Once I threw that sleep in there, it cleaned it up, and we got what I expected, which was an ASCII string. And so now we've got our tunnel up so that we can communicate with it. And we've got our script, which I pulled from that website. Now I've modified it so we removed some of the web-based stuff, and some of the web server-based stuff. And so instead we're creating a socket, we're connecting it to our localhost on port 1337, and that's in the initialization function of this class. So when we create an instance of the class, I added a little string here so we can see what we're doing, where it's going to print out the base 64 encoded version of the data that it's trying to test against the Oracle. This is something that I'm trying to do. I didn't actually try this in my original one, so this may completely fail and we may have to sleep anyway. I'm hoping that I can remove the sleep so that we can see this in real time. So R is just the response from the server. I'm setting it to nothing here. Then we send our data. Actually, I just saw a problem with this that I didn't notice originally. So this probably won't work without a sleep still if we're getting partial reads on the server side, because basically this is going to do a send of data each time we do a receive. And so what I was trying to do here was have this set to nothing, send, receive. If the new line isn't in our receive, means we didn't get it all yet. So continue, which will cause us to jump back up here. But the problem then is we send again, we receive again. So I would need to find a way to comment or to not do this send a second time if our receive, which actually we can do that real quick, I think. If R is not equal to, or if R is not, this is a problem with moving between tons of languages, as I always forget the syntax for simple things like that. But I think this will work. So if R is not nothing, we want to do if R is nothing. So if R is blank, we'll send. Otherwise, if R is not blank, if we got some partial read, we won't send. We'll just do our receive again. So maybe this will work. And then if it gets the word error or the word padding, which is what we saw when we were doing these tests here, we get generic error if we send just complete garbage. We get invalid padding if we screw up the padding. So if we see error or padding, we raise a bad padding exception, which will cause it to continue on its iteration. Else, if everything was good, it'll return. And then basically what we're doing here, this is just some default stuff that we're actually going to ignore because it doesn't, we changed the way this started up a little bit. So I'll just do oops, no, we'll just leave that alone. So the logging set to debug, encrypted value right now is set to nothing. We create a new pad buster, we do decrypt, and we do our encrypted value, which actually I think we need to base 64 decode it first. B64 decode because it's already encoded when we input it in. The other thing that we saw differently was the default script had 8-byte for both the IV and the block size. I don't think that's right. I think if I remember correctly, it was 16 bytes. And I think AES specifies 16 bytes as the minimum size anyway. 8 bytes isn't a valid block size. I think you can do it, but I think as far as the spec goes, it's not. And then when it's finally done and we get value, it'll print it out. So all we need to do now is paste in this base 64 encrypted string, which is our starting point. I guess muting the microphone worked out well because I chopped about 9 minutes off of getting to this point by not talking slowly while I'm typing, which is what normally happens. Let's just clear this out. Actually, let's clear this all out because we're not going to be passing arguments in. So I think we're good to go now. Now we may still need to end up adding a sleep, but hopefully that fixed that problem. We'll call this pad buster.py. And we'll run it in here so that we get a better view. Python pad buster.py. And so we can see now that these byte values for this particular block are being incremented. And so what it's trying to do is it's trying to find valid padding combinations, which it just found something, and so it's moving on. I'm going to go ahead and pause while this runs, and I'll unpause when it's finished. And so it looks like my fix didn't work. We're bailing out byte 15 not found, and so I'm guessing that we're having an issue with decoding again because of the fact we're doing this over a socket. So what we'll do is a temporary fix again. In real life, I would probably just package this in real life. if I was doing this for the first time at this point, I think I would just package this up and pull it over to Smasher itself and run it there because it would be a lot faster. Because this is for a video where I have the ability to just pause it and you guys don't have to wait through the painful waiting, I'll just stick a sleep in there for about 100 milliseconds, which I think is about what my latency to the server is, and that should be enough to correct the issue. And so we'll get this running again and we'll see what happens. And so it just finished decrypting the final block, and as we can see here, it decrypted to SSH password for user Smasher is padding Oracle Master 123. And so if we take this now, and by the way, when I was doing this originally, some other things I had tried, of course, is hoping that it was as simple as, since it was a Python script, that they were using Python 2 and were using input or something, so I tried to see if I could inject Python commands, which you can't. I didn't show that here just because I felt like it was, sorry, let me type this and then I'll talk. Smasher at 10, 10, 10, 89. Felt like it wasn't really worth showing, but just in case people were wondering, yes, I did try and do that. So we are in as Smasher now. And so I believe the user text is in here, so if we cat user.text, and we will pipe that to cut C1 to 16, so you can only see the first 16 characters. And so we've now got the user flag on here, and so now we need to get escalation to root. And our first place to go is that checker executable that we saw. So if we run checker, now we can run it. It says welcome to file UID checker 0.1 by Dzonerz. I don't know how to pronounce it. Dzonerz. Anyway, so it looks like we're able to pass it a file. So let's just do checker user.text. Oh, oops, that was a bad one to do. I'll have to edit that one out after the fact. I wasn't thinking. But basically it shows the file UID and it shows the data that's contained in the file. So if we do like checker socat.sh, so same thing, checker user bin sudo. And so in this case, it looks like it just outputs elf, and then that's it. My guess is probably because it's doing some sort of a string copy, and when it hits nulls, that's it, because I think an elf header has elf, and then some nulls, and then some other stuff. And so we basically have to figure out a way to get a privilege escalation with this. And so we could try and load it up in like a debugger and do something, but the issue with that, if you're not aware, is that you can't use ptrace inside of SUID executables, and so we actually would, even if we could do something creative in there, like see the contents of a file before it did a check or something, it wouldn't help us because of the fact that basically we would drop privileges when we load it up in there. So what I'm doing is I'm opening up Hopper. Hopper's a cheap disassembler. It's not as good in my opinion as IDA or something like that, which I also have, but I figured showing how to use IDA for this isn't as good because it's so expensive. It's prohibitive for most people. There is the free version, but that's fairly old. And Hopper's pretty cheap. It's like 99 bucks or something, and it's pretty good. So if we go to read executable for disassembly, Dropbox, CTS, Hackthebox videos, Smasher, and Checker, which I downloaded before. We hit OK, and so we can see a disassembly of it. We can find main, and go to main, and so we can see here, we can see our variables that were pushed on the stack. This has a handy little pseudo code view that actually for a lot of stuff is pretty good, so we'll hit that up. And we'll see main, we've got arg0, arg1, arg0 and arg1 we could actually rename. I don't know how to rename them in this pseudo view, which is kind of annoying, so it would have to pop back over here. But you can see that var var224, 230 are being set to these two. So var224 is argc, and then 230 is argv. And so we could pop back over here, call 230 edit variable, call this arg. I actually don't remember which one this was. argv, I think. So it's probably a character pointer, although I don't know the setting that matters. We'll just say okay. Yeah, and so arg224 is argv. And you don't have to do this, but, or sorry, it's argc. I like to because it makes it a little easier to read when you're looking through over here when things are used. So like here, if argc is greater than 1, then it's going to do this, else it's going to output that it's missing arguments. And so I feel like that makes it a lot easier, at least for me, to read through stuff. So if we look through here, first thing we're doing is get UID. If it's not 3E9, which I think is 1001, then it thinks we're not Smasher, and so it gives us the we're not Smasher bro, and sets RAX, which is our exit code, to all Fs, which is -1, I think. And else it continues on, does that welcome message we saw. If argc is greater than 1, then it's setting 8 to a pointer of argv plus 8. So argv itself would be a pointer to the executable that we're running. This would be the first argument, and so it's basically grabbing the first argument in this and setting it to var8. And so the first argument is the file name, and so we could bounce back here. We could rename this file name. Bounce back into here. So now we can see that file name is here. This malloc is setting memory, let's see, 90. If we look at how it's used, var10, it's used in stat. So stat takes a structure. I think if we just do man stat, it actually doesn't help because that's the wrong stat. Stat. So it takes a structure, a stat structure, and it's called stat buff, so we'll rename that stat buff. So var10 is a stat buff. So edit variable stat buff. Oops. Buff. So we're allocating a stat buff. We're calling stat, making sure that it's equal to 0, 0. So the exit code on this is returns. On success, 0 is returned. So as long as we get success, we're continuing on. Next thing it does is an access check. 04 is read, I believe. So you can look that up. So it takes a path name and a mode. In the mode, I don't know that it's actually breaking it down here, but that's all right. 4, I believe, is just a read access. And so what it's doing then is it's looking for read on success. 0 is returned. So it's basically doing the same thing, seeing can it read it. If it is, 0 is returned. And we can see here that it's passing the file name, or it's passing, the file that we want to read. It's doing a set. Oops, I didn't actually want to go into that. It's doing a set UID to 0, which is root, set GID to 0. It's doing a sleep, and this sleep's a little weird, but for whatever reason it's doing a sleep. Then it's doing a string copy. It's passing the address of var20, and it's calling a function called read file name. And so we do string copy now, strcpy, which if people are familiar with it, string copy is unsafe because it just keeps on going. So it's got the destination and then the source. So we are copying from the output of this read file, which we'll look at in a second, and we're writing it into var20. So we'll rename var20 our destination buffer, dstbuff. And so read file looks like it's just, let's see, I won't actually rename these ones because it's adding more time. So var8's set to 0, var10's fopen arg0, which is our file name. And don't know what, let's see what the second argument to fopen is. I should know this, but oh, it's a mask for the file open. And so if var10, which is the handle from fopen, isn't equal to 0, then it's seeking to 0 bytes from x2, which is the end of the file. So it's seeking to the end of the file, doing an ftell, so it's getting, okay, so all this is doing is getting how big the file is, basically getting the number of bytes in it. It's rewinding back to 0. It's doing a malloc set to the number of bytes plus 1. Then it's doing an fread, so it's basically just reading in the file, and it's going to return a pointer to the memory that contains the bytes from that file. And then those are going to be copied into this destination buffer. So if this is bigger than that, then we're going to overwrite this. Our destination buffer, I think we can see it in here at the beginning of main. Yeah, it's 544. So it's 520 bytes. And so if we send it a file that's bigger than that, then it's going to overflow. You see printf, and so this is where we're printing the UID, printing out the contents. Else we've got these checks of these different if statements failed, and then we're returning. So it's pretty simple. This one's actually really easy to look at. It's a good example of how you can reverse a binary that's fairly simple anyway to figure out exactly what it does. Hopper is great for that. So we'll minimize this, and we'll try and run it on our local system here real quick. I guess I've got SSH sessions in all of them, so let's exit out of this one. Checker chmod plus x checker. I don't think we can run it yet. Yeah, because we're not Smasher. I think I did create a user on this box when I was doing this originally. But it's Smasher, so we su Smasher. And then we run it. And so let's try just doing something simple like echo or python-c print a times 1,000. And we'll write that to overflow.txt. Oh. I apparently can't type it either. Oh, that's right. su root. So this is a problem when you're working in the wrong directory where Smasher, the user, doesn't have any permissions. So let's do this. Let's make a directory temp, Smasher, chown, Smasher, smasher. Now let's switch to smasher. Let's copy our checker over there. We won't worry about set UIDing it yet. So now if we do that Python command, so now we've got a file to send to it, so we do checker overflow.txt, and we get a segmentation fault. So if we do gdb checker, and we do start overflow.txt, oh, and we don't have PETA installed under Smasher. I'm actually going to do that real quick because it'll make it easier to show. Let me see, I think I can probably do it fast enough that I can show you how to do it since I didn't show in the beginning. PETA Python. So there should just be a series of like 3 commands that we can use to install it, which is right here. Copy that. Oops. Copying between terminals and the web browser screws me up a lot. Oops. Apparently I didn't copy it. Okay, so now if we run, now we've got PETA, so if we do start overflow.txt, so we hit a temporary breakpoint, we continue, we get our seg fault, we take a look here and we can see that we've overwritten a bunch of stuff with our A's. RSP though isn't pointing directly into our buffer, it's actually pointing to a pointer that contains our buffer. And so, let's see here, if we just do quit msf pattern create L1024 pattern.txt, run it again, start pattern.txt, continue, get our seg fault, print out the value at RSP, and unfortunately it's just a pointer. If we print out the value at that pointer, this should be what we want to check. So if we run msf pattern offset, query that, exact match is at 767 or 776. Again, for the sake of keeping this video short, I'll just go ahead and cut to the chase. I wasn't able to get the buffer overflow to work on this. No matter what I did, I wasn't able to actually get control of RIP. So we're going to skip this because it didn't work for me. If you made it work, great. I ended up going back to Hopper, taking a look through here again, trying to ignore the buffer overflow this time and see if there was something else that stood out. And what I noticed, as I pointed out before, is this sleep seems a little suspicious. We've got a 1 second sleep here, and why do we have a 1 second sleep? Well, I think the issue that we have here, or I know the issue that we have here since it's able to exploit it, is a time of check, time of use race condition. And so basically what that is it's a race condition where you're able to change something between the time that permissions were checked and the time that they actually used whatever that thing was. And so in this case, it's this access. This access looks, it says, hey, is this person able to read this file? If it comes back yes, then it says great, good to go, sets all this stuff up, sleeps for a second, then reads from the file. So in theory, if between the time that this says, is this guy able to read this file, and it says yes, if we can change out what that file is between here and here, then it's going to go ahead and read it whether or not we have access to it, because remember, this is a set UID executable, and so it's running as root, it can access anything. And so it will be able to read it it'll read it and it'll output the data in it. And so we can use this to read the root flag. I didn't figure out a way to get a root shell on here, which kind of kills me, but I didn't have a lot of time either. I actually ended up doing this box just before I found out that it was retiring. I hadn't tried it before, and so it was kind of a mad rush, which is why this video has also been kind of a mad rush. But so what we'll do is we'll see if we can just execute this, or take advantage of this race condition. And rather than write a script for it, which you're welcome to do, I'm sure that's what most people did, this 1 second sleep's big enough that I think we can just manually take advantage of this. Let's see if I can make this work on the first try. So on Smasher here, let's just do second terminal. Don't remember if, no, I have that in there. So we need the password for Smasher. So SSH Smasher at 10.10.10.89, and it was padding Oracle Master 123. Let's just get these both cleared. Let's switch into some temp directory, dev shm test, just dev shm, I guess, cd /dev/shm. So let's echo testing into anchor, and then let's lns pivot anchor, anchor pivot. So I cat pivot, get testing. And so then what we need to do, I believe, is just do on this window a ln-sf, and then /root.text. And then if we do checker /dev/shm/pivot. Oh, sorry, almost screwed that one up. /dev/shm/pivot. And so what we're doing over here is we're changing the symbolic link that pivot currently has, which is to anchor, over to root.text. And we're going to try and do that in that 1 second that checker is sleeping. And so if this works, we should be able to read root.text. And so I'll basically just hit enter, enter. And I screwed something up. ls. Interesting. So for some reason it doesn't work in shm anchor. Oh. Checker dev shm anchor. So it is able to read anchor. I don't know why it's not able to read pivot. Cat pivot. Interesting. So maybe it has something to do with this directory. Let's switch to temp. Let's do the same thing. Echo testing anchor. Go testing to anchor. -s. Anchor to pivot. Checker pivot. File does not exist. Well, let's try it in his home directory, I guess. pivot. Okay, so that works. I don't know why it's not working in the temp directories. But we can probably work with that. sf dev, not dev, sorry, home, smasher, pivot to root.txt, checker pivot. So we'll just hit enter here, hit enter there. Failed to access root.txt, that shouldn't matter. Oh, we're still working in the wrong directory though. Oh, this is a wrong account. SU smasher, and then we just need to add in Oracle master 123. So that should work a little better. Okay. So now sf dev, sorry, home smasher pivot to root.txt and checker pivot. So still failed. Let's see if it's still pointing to. Oh, I see what I'm doing here. Simple mistake. Our source is root.txt and we want to still link that to home smasher pivot. So I was getting my operands in the wrong order. Checker pivot. So hopefully this works. And there we go. We have the root flag. And so we could have done that with a script or something, which I'm sure a lot of people probably did. But in this case, that 1 second sleep is big enough that you can just do it manually as long as you have your operands on creating the link correct and you're on the correct user account and yada yada. Anyway, it's been an incredibly long video. I am going to be totally impressed if people actually watch the entire thing because it's like Titanic length. I'm going to try to see if I have time to edit this up into kind of a series also, so that if people want to watch it in kind of pieces, where I'll do the first part where we just explore the buffer overflows that get us into the www account, and then where we did the padding oracle attack, and then finally where we have this piece. And that way it's a little bit more manageable. And if people are looking to learn about just a specific thing, I may even break the buffer overflow into the traditional executable on the stack and then the return to libc. That way people can just see those pieces if they want to. I'll also try and do a good job of putting shortcuts in the video description so that you can jump around to where you want to see. And so anyway, that's it for this box. This is my favorite box on Hack the Box so far. Granted, there's a bunch I haven't done still because I just don't have time, but at least from the ones that I have done, this is by far my favorite. And it was difficult, which I think is why I liked it so much. Anyway, I hope you enjoyed the video. Thanks for sticking around through the whole thing. Make sure you like and subscribe, and follow me on Twitter or Hack the Box. Message me on Hack the Box. You can't follow me. Anyway, have a great weekend or whatever day it is, and I will see you in the next video.